PU2 champions, welcome to Dhurandhar series, and in today's class we are going to solve the most important questions from the chapter Electrochemistry. Now these questions are sourced from PYQs and the question bank that is released by the PU2 board for 25-26. Now if you just watch this one video and practice the questions, then you will be able to attempt all the questions asked from this particular chapter in your exam. So before starting the questions, let's understand the blueprint or the weightage of this chapter. So electrochemistry has a weightage of, just a minute, yes, electrochemistry has a weightage of 13 marks. Okay, now how is this 13 marks distributed? So you can see that there will be one marker question. Okay, either it will be in the form of MCQ or FIB. There will be two theoretical questions and there will be two numerical questions. Okay, so that is how you have to attempt this. Now let's move and discuss the previous year questions. So I have considered 2025 to 2022 papers. So let's see what are the questions being asked. The first question is, write a neat level diagram, cell representation and the half cell reaction of standard hydrogen electron. Okay, this is very important question. Thousands of times it has been asked. So first of all, well level diagram of SHE. So you can see this is a well level diagram. Here you have to level the hydrogen gas and its pressure. Then you have to level this particular the platinum, finely divided platinum coated on the platinum foil. Okay, so this is a platinum wire on which there is a platinum plate. In this platinum plate, platinum powder is plated, okay, to increase the surface area, to increase the adsorption of hydrogen gas. And next what we see here, this is the solution which is present. This is 1 molar H plus concentration. So this is how we can draw the well level diagram. The next part is to write the cell representation. So you can see platinum wire is there. Okay, so platinum wire, then on that hydrogen gas is there and it is reduced to H plus. So H2 to H plus, that is the I can say cell representation. Next, you also need to write the half cell reaction. So hydrogen undergoes reduction here. So H plus plus 1 electron gives you half H2. Okay. Now let's see the next question. Okay, before moving ahead, so I just want to remind you that, my dear children, this 30 days, whatever is left, I think not even 30 days is left for your final exams, and almost 83 days are left for your KCET 2026 examination. Now these days which is left, right, this last phase, this last moment is very crucial and should be used very effectively. Okay, and I can understand that at this point of time many of you will be going through stress, confusion, you will be having self-doubt, you will be having doubt on your resources, your study strategy, whether you will be able to get the results or not. There will be so much confusion around you at this point of time, and I can understand well, because all of us, because I have also gone through this phase and have cracked the I can say competitive exam as well as the board exams. So if you need any guidance in this particular period, if you have any doubt, you need any type of guidance, strategy, personalized plan, I am there to help you, and I will be the best person to help you, because I have been mentoring KCET and PU2 students for last 3-4 years and have guided thousands of them to top rank. So definitely you can trust me, and if you want to get benefit of this mentorship session, you can click on the link given below in the description section and register yourself. And once you register, we will be having a one-to-one session where I will be helping you with all your doubts, starting from your personalized plan, study strategy, chemistry academic doubts, how to move ahead from here. Wherever you are stuck, after this interaction, you will come out of that and you will get a clarity about your preparation. So if you have any confusion, do not hesitate, just register. Okay, now let's move to the next question. So next question of PYQs 2025 March. So this is the recent year paper. Lead storage battery is commonly used as a secondary cell in automobiles. What is a secondary cell? And write down the reactions that occur at anode and cathode during the discharging of the lead storage battery. So the question is asked, first of all, what is a secondary cell? So you know batteries are divided into two types, primary batteries and secondary batteries. Primary batteries are those which cannot be used again, whether secondary batteries can be reused by passing current in the opposite direction. So that is what you have to write. A secondary cell after use can be recharged by passing current through it in the opposite direction. These are the key words which I am underlining. You need to underline those words in the exam. That will create a good impression. Next is, during discharge, the anode reaction, oxidation. So lead gets oxidized here. You can see Pb in the zero oxidation state gets converted to Pb plus 2. And at cathode reaction, Pb in the plus 4 state gets reduced to Pb plus 2 state. Okay, so there is a reduction of PbO2 at the cathode and oxidation of Pb at the anode. Okay. Now moving to the next question, this is a numerical question. The standard electrode potential of the Daniel cell is 1.1 volt. Calculate the standard Gibbs energy. Okay, so you know Gibbs energy formula is delta G is equal to minus NF E naught of the cell. Okay, what is the value of N here? You can see Zn gets converted to Zn2 plus 2 electrons are used. Copper 2 plus gets converted to copper 2 electrons are used. So N value here is 2. So just we need to substitute that. So I'll show you just a minute. So I have already calculated the answer, so that because here you don't have to worry about calculation, because we will be having calculator in our board exam, so you can easily do all the calculation. So we have this one, F is equal to 96500 coulomb. So delta G is equal to minus NF E naught of the cell, and that is equal to minus 2 into 96500 into E naught of the cell is 1.1 volt. Now, if you solve this whole thing, you will be calculating around minus 212.3 kilojoule per mole. Okay, just check this calculation, you will get this answer. Moving to the next one, 2023 March paper on charging the lead storage battery, PbSO4 on cathode is converted to. Okay, now see here what happens. See, if you have seen on charging, means the reverse reaction will happen, right? At cathode there will be I can say oxidation, and at anode there will be reduction. So PbSO4 is converted to PbO2. The reverse reaction happens at cathode. So PbO2, there will be oxidation from +2 to +4. So A is the correct answer. Okay, next is another numerical question on basis of Kohlrausch law. Lambda, molar conductivity of NaCl, HCl and NaAC are given to us. Okay, these are the certain values. Calculate the molar conductivity of HAC. Okay, now see, to solve this question, you just need to know that molar conductivity, see how to solve this question. See, you need to know that molar conductivity of HAC is equal to molar conductivity of H plus molar conductivity of AC minus. Okay, now I need this H plus, and what are the values given to me? I have been given with molar conductivity of NaCl, which is equal to molar conductivity of Na plus and molar conductivity of Cl minus. Then we have been given with the molar conductivity of HCl, which is again equal to H plus and Cl minus. Okay, then you have been given with NaAC, which is equal to molar conductivity of Na plus and AC minus. Right, so now I want this H plus, right? So from which equation I get? From the second equation. So take this one. So lambda of HCl you will take. Okay, then you did AC, means where I will get AC, you can see the third equation. So I can write NaAC. Okay, now see, when you add these two, H plus is there, Cl minus is there, Na plus is there, AC minus is there. So H plus and AC will be there, and extra NaCl which is not required is also created here. So to remove that, you have to subtract here for NaCl. Okay, now if I put all these values, so NaCl is how much? For 126.4. Okay, HCl is 425.9. Okay, and NaAC is 91. So HCl is 425.9. Okay, NaAC is 91 minus 126.4. Now if I solve this, you will get 390.5 something. Okay, I'll just now clarify, I'll just clear all so you can see. So you will get around 390.5. Okay. Next, third question is also a numerical question. The first part is the numerical one. Calculate the standard Gibbs energy for the given reaction. Okay, now you see E naught of zinc is given and E naught of silver is given. Okay, and how to calculate E naught of the cell? E naught of cathode minus anode. But where here, how will you know which is cathode and which is anode? See, zinc is undergoing oxidation, right? 0 to 2 plus. Zinc is undergoing oxidation, and oxidation happens on anode. So zinc has to be the anode, right? And you can see silver is undergoing reduction, right? So that means this one has to be the cathode. Okay, so I will subtract cathode minus anode. So what is E of the cell, or E naught of the cell, is equal to E naught of cathode minus E naught of anode. Okay, so now let's see this one. In this, how many electrons are used? So first of all, what you need to do is to calculate the E naught of the cell, cathode minus anode. So silver minus zinc. So silver value is 0.8 volt and zinc value is minus 0.76, and when you add this, it get 1.56 volt. Now delta G is equal to minus NF E naught of the cell and the number of electrons used here, n value is equal to 2. So I'll have 2, then 96500, and E naught of the cell is 1.56 volt. Now when you multiply all this, you will get minus 301.08 kilojoule. Okay. Next, we'll see the B part. Write the balanced equation for the reaction taking place at anode and cathode during the rusting of iron. Okay, during rusting of iron is an electrochemical phenomena. So what reaction takes place at anode and cathode, that we will see. So at anode, what happens? Fe gets oxidized to Fe2 plus with the release of 4 electrons, means 2 Fe. And at cathode, what happens? Oxygen gains this electron with hydrogen to get to form water molecule. Clear? That is the reaction at anode and cathode. Okay, next is May 2023 paper. So how much electricity in terms of Faraday is required to produce 1 mole of aluminium from Al3 plus ion? So if you see, Al3 plus ion gains 3 moles of electrons to produce aluminium, right? So 3 moles of electrons means 3 Faraday. So that is option number C here. Next, what are fuel cells, and write the electrode reaction taking place at the cathode of H2O2 fuel cell. Okay, so now see, galvanic cells are what? In which the chemical energy is converted to electrical energy. Now the Daniel cell which we have studied, there the chemical energy comes from redox reaction. Okay, but if there can be certain galvanic cell where the chemical energy that comes from is the combustion of fuels, and that is converted to electrical energy, that is called as fuel cell. So you can see galvanic cell which are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called as fuel cells. And just the cathodic reaction is asked. So at cathode, oxygen gets reduced. So O2 plus 4 electrons with 2 water gives you 4 OH minus. Okay. Next, question number 6 is a numerical from Nernst equation. Calculate the EMF of the cell in which the following reaction takes place. Mg plus 2Ag plus gives Mg2 plus 2Ag. E naught of the cell is already given. Okay. So we know what is the, so I'll first explain, then I'll show you the answer. So E of the cell is equal to what? E naught of the cell minus 0.0591 by N log of product concentration by reactant concentration, right? So product concentration is magnesium, so 0.13 divided by silver concentration, you can see there is 2, right? So there will be a power of silver as well. So this is 10 to the power of minus 4 to the power of 2. Okay, this has to be the value. And here if you see, magnesium loses 2 electrons, so N value is 2. Silver gains 1 electron, 2 silver is there. So here N value will be 2. And E naught value is 3.17, right? So now I can just show you the substitution here in detail. You can see E of the cell is equal to E naught of the cell, that is 3.17 minus 0.0591 by 2 log of 0.13 by 10 to the power of minus 4 square. Now if you just solve this, it becomes 1.3 into 10 to the power of 7, right? Now 3.17 minus 0.05. So if you want to see this value, okay, the log of 1.3 into 10 to the power of 7. Now we know that log AB, okay, is equal to log of A plus log of B, right? Now log of 1.3 into 10 to the power of 7 is equal to log of 1.3 plus log of 10 to the power of 7. Okay, now log of 10 to the power of 7 is definitely 7, and log of 1.3, how will you calculate? So if you see the log table in 13 value, this value is 1139, right? So see, you have to just take 13, there is no decimal or no number after 13, so you have to check this number 1139 and put a decimal before that, so that is 0.1139. So I'll get 7.1139, which can be written as 7.114. Now if you just solve this, you will get 2.96 volt. Clear? Now we will see next question. State the Kohlrausch law of independent migration and mention one application of it. This is also a very, very important question. So Kohlrausch law, what it states that at infinite dilution, the molar conductivity of the electrolyte is due to the sum of the limiting molar conductivity of its constituent ions. Means, for example, NaCl is there. The limiting molar conductivity of NaCl is the sum of the conductivity of Na plus and Cl minus. So that is how it is represented here. And application, it is used to calculate the molar conductivity of weak electrolytes, and it is used to degree of dissociation of weak electrolytes. Okay. Next, we'll see question number from PYQ 2022 now, March. Give an example of inert electrode. Mention in 2 applications of Kohlrausch law. What is molar conductance and how it is related to the concentration C and conductivity K. Okay, so what is an electrode? Example, you can give platinum or gold electrode. Applications of Kohlrausch law, just now we saw, it is used to determine the molar conductivity of weak electrolytes. It is used to calculate the degree of dissociation and dissociation constant for the what I'll say, for the weak electrolyte. Next, the relation between, so what is molar conductance? It is the conductance of all the ions produced in the entire solution which contains 1 mole of electrolyte. Okay, so the conductance of all the ions present in 1 mole of an electrolyte is called as molar conductance. And lambda m, the formula is kappa into 1000 by C. Okay, where kappa is your conductivity. Okay, kappa is conductivity and C is concentration. Okay, and lambda m is nothing but molar conductivity. Okay, fine. Next is question number 4. Calculate the value of delta G at 298 Kelvin for the reaction. So you have been given E naught value of Mg2 plus 2 Mg is minus 2.37 volt, and E naught of copper is 0.34 volt, and Faraday value is given to you. You have to calculate the value of delta G, and we know delta G is equal to minus NF E naught of the cell. So the first task here is to calculate the E naught value, right? And how to identify which is cathode and which is anode? See, magnesium is undergoing oxidation, so definitely this has to be anode. Right, you can see Mg is going from 0 to plus 2. Now copper is going plus 2 to 0, so that means it is undergoing reduction. Okay, so that has to be your cathode. Okay, so cathode minus anode, so plus 0.34 minus 2.37 volt. Okay, so you can see E naught of the cell is E naught of copper minus E naught of magnesium, so plus 0.34 minus 2.37, which gives me 2.71 volt. Okay, now suggest any two methods. Okay, so once you have got this one, then we have to calculate the delta G value minus NF E naught of the cell minus 2,96500, and E naught of the cell is 2.71. Now if I multiply these all things, it is minus 523.03 kilojoule. Okay. Next, suggesting two methods to prevent the corrosion of iron. The first method is painting and the second method is galvanization or coating the iron with zinc. Next, mention any one method for the prevention of corrosion. Already we have discussed. Write the symbolic representation of standard hydrogen electrode and mention the value of E naught of SHE. Okay, let's do first this one. So the first method of prevention is covering the surface with paint or other metals like tin or zinc. The next one is to write the symbolic representation: platinum, hydrogen gas 1 bar and H plus 1 molar. And what is the value? Value of E naught is 0 volt. Next, how many Faradays of electricity are required here? So you can see this is plus 7. Okay, plus 7 to plus 2, 5 moles of electrons are gained, so 5 Faraday. And plus 3 to 0, 3 moles of electrons are gained, so 3 Faraday. Okay. Next is for a galvanic cell, Mg to Mg2 plus gives 0.13 molar, Ag plus to Ag. Write the overall cell reaction and calculate the E of the cell at 298 Kelvin. E naught of the cell value is already given to you. Okay, so now if you want to calculate this one, that is E naught of the cell, E of the cell, we will again use Nernst equation, right? So for using Nernst equation, I'll first need to write the reaction here. See, I'll tell you at anode what is the reaction. Mg is undergoing oxidation, right? At anode, the reaction is Mg is undergoing oxidation to give you Mg2 plus 2 electron. And at cathode, what is the reaction that is undergoing here? 2 Ag plus, I'm writing 2 because I have to gain 2 electrons to give you Ag, 2 Ag, right? Now what will happen? These two will get cancelled, and the overall reaction that I will get is magnesium plus 2 Ag plus, okay, gives you magnesium 2 plus 2 Ag. Okay, now this is the final reaction that we have. Now for this one, you need to write the E of the cell and E naught of the cell. So E naught of the cell value is minus 3.17 volt. Okay, so I'll just clear now so that we got the final equation here. Now you can see E of the cell is equal to E naught of the cell minus 0.059 by 2 log of magnesium 2 plus the product ions divided by the reactant ions to its power. So now I have substituted all the values. So now if you see, you will get around 2.96 volt. Okay, this question we have already solved a similar question. Next, what is a secondary battery? Already discussed, the battery that can be recharged by passing current in the opposite direction. Now we will do the question bank questions. Okay, so there is no 2-3 markers separately. They have asked it together. So I have taken almost all the questions of the question bank, okay, the theoretical questions. So let's see the first one. What are electrochemical cells, and mention the types of electrochemical cells. So what are electrochemical cells? These are is a device in which the chemical energy is converted to electrical energy by a redox reactions, right? Next, types of electrochemical cell, you have galvanic cell and electrolytic cell. In galvanic cell, the chemical energy is converted to electrical energy, and in electrolytic cell, the electrical energy is converted to the chemical energy. Next is, how do you differentiate between galvanic and electrolytic cell? So there can be 3 to 4 points of difference. Galvanic cell, first of all, converts chemical to electrical, whereas electrolytic cell converts electrical to chemical. Okay. Next, this is spontaneous reaction. This is non-spontaneous reaction. External power is not required. Here, external power is required. Anode is negative, cathode is positive. Here, anode is positive and cathode is negative. Okay. Any 2 to 3 points of difference you can write down. Next, how do you represent a Daniell cell symbolically? Write the electrode reactions and the overall cell reaction. Okay. So Daniell cell is represented symbolically like this: Zn, Zn2 plus, then salt bridge, copper 2 plus, and then copper. And what is the anode reaction? Here you can see zinc is undergoing oxidation. So Zn gives you Zn2 plus 2 electrons. Cathode copper 2 plus 2 electrons gives you copper. Then what is the overall reaction? Just add these two. So you get Zn plus Cu2 plus gives Zn2 plus Cu. Okay. Next is, what are the functions of salt bridge? So, okay, functions of salt bridge, here I have written 4 functions. You can remember any 3. Maintains the electrical neutrality, completes the electrical circuit, prevents the mixing of the electrolytes, and minimizes the liquid junction potential. Next, what would happen if no salt bridge were used in an electrochemical cell? Why is it necessary to use a salt bridge in a galvanic cell? Okay, both the questions will have the same answer. So if the no salt bridge is used, then what will happen? The positive and negative charges will accumulate in the half of the cells, right? This particular function, which is the maintain the electrical neutrality, that will not occur. As a result, what will happen? The flow of electron will stop, and that is why the cell will stop functioning. Okay. Next is, next we'll go to, what is the effect of the change in concentration? What is the effect of change in concentration and temperature on the electrode potential of a given half cell? Okay. Now, if you see electrode potential formula for Nernst equation, suppose if I write, it is E naught minus 0.059. Okay. If you remember this, I'll write the full formula. It has come from 2.303 RT by NF log of, okay, 1 by concentration of the ion, right? So now what happens? What is the effect of change in concentration? So if you increase the concentration, then what will happen? This whole term will 1 by Mn plus will decrease, right? And the whole term will decrease, and this whole term will decrease. So that means you are now subtracting this whole term. This whole term will decrease if you increase the concentration of Mn plus. Now see, you can see if this one will go higher, this value overall will become lower. Log of that value will be further lower, and this whole multiplied value will be lower. Now, when you subtract E naught, so you are subtracting a lower value now. So what I can say, if concentration increases, then E naught value, E value will also increase. Now, what happens if temperature increases? If temperature increases, this overall term becomes higher, right? That means now you will be subtracting a bigger number. So the E naught or E value will decrease. So if temperature increases, E value will decrease. So let's see that. So electrode potential depends on the concentration of ions in the solution. Increase in concentration increases the electrode potential. I have already explained how. Decrease in concentration decreases the electrode potential. Temperature effect, electrode potential changes with the temperature. Electrode potential decreases with the increase in the temperature for most of the cells. You can see temperature is in the numerator, right? So when you increase the temperature, this overall value becomes a bigger number. Now you are subtracting a bigger number from E naught value. So E value will definitely decrease. Next, fourth question, what is an electrochemical series? How does it help in predicting whether a redox reaction is feasible in a given reaction or not, in a given direction or not, and how does it help in calculating the EMF of the standard cell? Okay, so what is an electrochemical series? First of all, electrochemical series is the arrangement of the elements in the increasing order of their reduction potential. Okay, from lower to higher, the reduction potentials elements are arranged in their reduction potential value. A redox reaction is feasible, the first one, right? How will you say that whether the how from this particular electrochemical series, we can say that whether the reaction is feasible or not. See, a redox reaction is feasible when the substance with higher reduction potential acts as cathode. Okay, substance with higher reduction potential acts at cathode, and the substance with lower reduction potential acts at the anode. If the calculated cell EMF is positive, then the reaction is feasible in that direction. The standard EMF of the cell is calculated using E naught of cathode minus E naught of anode. Here this E naught value are your reduction potential values. Okay, the values of the standard electrode potentials are taken from the electrochemical series. Okay, next is fifth one. Give the reason why blue copper sulfate solution is discharged slowly when an iron rod is dipped in it. Okay, E naught of copper is given and E naught of this one is given. Fe2 plus 2 Fe is given. Okay, now see, well, the question is saying that blue copper sulfate solution is discharged slowly. Means what happens if you have copper 2 plus and discharge means it gains electron to get Cu. Okay. Now see, since iron has a lower reduction potential than copper, iron gets oxidized. Okay. And copper ions get reduced. If you see in this particular combination. So Fe will undergo oxidation, copper will undergo reduction. So overall reaction is Fe plus Cu2 plus gives Fe2 plus plus U. Now see, as the potential difference is moderate, there is not too much difference between the iron and copper potential difference. The reduction proceeds slowly, hence blue copper sulfate solution is discharged slowly. The more the difference, the faster will be the reaction. Next, what is meant by the reduction electrode potentials of zinc and copper being these values respectively? Can an aqueous solution of copper sulfate be stored in a zinc vessel? Answer with the reason. This type of questions are asked often, so please understand first of all. Now, when you see a negative reduction potential, that means the element will undergo oxidation and not reduction. If the element is having positive reduction potential, that means it will undergo reduction and not oxidation. Okay. Now let's see first of all meaning, the first part. So you see minus 0.76 volt for zinc. That indicates that zinc has a greater tendency to lose electrons or get oxidized. For copper it is a positive value. That indicates that it has a greater tendency to gain electrons or get reduced. Now the second part of the question, can copper sulfate be stored in a zinc vessel? Okay, you are having a zinc vessel made up of zinc and here you have what solution? Copper sulfate. Okay, now see what is the tendency of the copper? Copper has a higher tendency to get reduced, right? Now see, zinc, that means what? Zinc has a tendency to oxidize. Okay, zinc has more tendency to get oxidized. So if you have copper sulfate and zinc, so obviously zinc is more reactive than copper. So zinc will displace the copper from its solution. Okay, it will easily reduce the copper. Okay, so zinc will displace copper from copper sulfate solution. Since zinc is more reactive or lower reduction potential, it corrodes the vessel, hence copper sulfate cannot be kept in a zinc vessel. Okay, the reverse can happen. Zinc sulfate can be stored in a copper vessel, but not the inverse one. Now let's see question number 7 here. Is it safe to stir silver nitrate with a copper spoon? Okay. Given the Ag plus Ag is 0.8 volt and copper is 0.34 volt. Okay. Now see, suppose we have a silver nitrate solution. Okay. This is a silver nitrate solution and we have a copper spoon. Okay. Now if you see, the copper is having lesser reduction potential, that means it will undergo oxidation and silver will undergo reduction. Right, that means copper is more reactive than silver, right? So easily copper can displace the silver, so we cannot use copper spoon with silver nitrate solution. Okay, so now let's see how to write this answer. Okay, so first of all you have to mention that no, it is not safe. Always write the answer first, what is it is safe or not. Next, silver has higher reduction potential than copper, so Ag plus ions will get reduced and copper will get oxidized. Copper spoon will dissolve and silver will deposit on it. Hence, it is unsafe to stir silver nitrate solution with a copper spoon. Okay. Next question, I2 and F2 are added to a solution containing 1 molar each of I minus and F minus. Okay. What reaction will take place given that the reduction potential of I2 and F2 are 0.54 volt and 2.87 volt respectively. Okay. So I minus to I2. Okay. See, I minus to I2 value is 0.54, okay, and F minus to F2, the value is 2.87 volt. Okay, now see, since fluorine is having a higher reduction potential, it will be undergoing reduction, and it will act as an oxidizing agent. Okay, and it will oxidize the iodide ions. So what will happen? F2 will undergo reduction to F minus, whereas I minus will get oxidized to I2. Okay, fluorine displaces the iodine from the iodide solution because it is having higher reduction potential. Okay, next we will see question number 9 here. How can the reduction potential of an electrode be increased? Okay, so we have already seen that reduction potential can be increased by increasing the concentration and decreasing the temperature. Already we have seen this question. 10th question, copper displaces the silver from the silver nitrate solution. Give reason. So we have already seen silver is having higher reduction potential. It will undergo reduction. Copper will undergo oxidation, so it can easily displace. Now copper has a lower reduction potential than silver. Okay, copper is 0.34 volt, whereas silver is 0.8 volt. Hence copper get oxidized and silver ions get reduced. So you have a reaction like this. Copper will get oxidized, silver will get reduced. Therefore copper displaces the silver from the silver nitrate solution. Next, describe the construction and working of SHE or the standard hydrogen electrode. Okay. Now, construction and working they have asked you. So, construction, you can see a platinum electrode coated with a platinum black is immersed in a 1 molar H plus solution. Then hydrogen gas is bubbled at 1 atm pressure and temperature is maintained at 298 Kelvin, and the volt that is taken here is 0 volt. And what is the working of this one? So the reaction H plus gains 2 electrons to produce H2 gas, and SHE can act as anode. The reaction takes place like this. When it behaves as a cathode, the reaction will be like this. So when the construction is asked, you must mention that there's a platinum electrode. You can imagine like this. Okay, and there is a platinum plate on which platinum is absorbed. Okay, and then this whole thing is present in a tube. Okay, and from this tube, what happens? The hydrogen gas is pumped out. Okay, or pumped at a pressure of 1 atm. Now this whole container is present in a solution of H plus, which has a concentration of 1 molar. Okay, and the standard hydrogen electrode, its I can say SHE value is 0 volt. Now let's talk about question number 12. Mention the uses of standard hydrogen electrode. It is used as a reference electrode to determine the standard electrode potentials. It is used to compare the oxidation or reduction tendency of other electrodes. It is also used or helps in determining the EMF of the electrochemical cells. Now give reason. Zinc displaces copper from copper sulfate solution. Zinc displaces copper from copper sulfate solution. So the reason here, because zinc has a lower reduction potential, right? You can see, than copper. So that means what? Zinc will get oxidized, and that is why it will displace copper. Okay, copper will get reduced and zinc will get oxidized. Zinc displaces hydrogen from HCl, but copper does not. Again, if you see, zinc is above the hydrogen, right? So zinc in the electrochemical series, zinc is more reactive, or zinc is having negative reduction potential, whether hydrogen is having zero potential value. So it can displace hydrogen from HCl to give you ZnCl2 plus H2. But copper lies below hydrogen, right? That means copper cannot displace hydrogen. So that is why it does not produce H2 gas here. Next, iron displaces copper from copper sulfate solution, but copper cannot displace iron from iron sulfate solution. Again, if you see, iron has having lower reduction potential of minus 0.44 volt, whereas copper is having plus 0.34 volt. Means copper will undergo reduction, iron will undergo oxidation. So when it undergoes oxidation, means it will reduce copper. So copper will easily get displaced, and copper cannot displace iron because it is less reactive than iron. Now we'll talk about conductance questions, measurement of conductivity of ionic solutions. Why is alternating current used in place of direct current in measuring the electrolytic conductance? This is very simple. That is because direct current changes the composition of the electrolyte. Okay. Next, what is conductivity, and mention its unit. SI unit. Conductivity means kappa value. Okay, so see, conductivity of specific conductance is the conductance of a solution placed between two electrodes of unit area separated by unit distance. Okay, two electrodes are there, they're separated by unit area, their cross sectional, the area between, so they're separated by unit distance, and the area between them is 1 unit area, and whatever electrolyte is present in this much place, and its conductivity is called as kappa value. And SI unit is S meter inverse, the SI unit, but we generally use S centimeter inverse. Next, write the expression for cell constant and write the SI unit of specific resistance. Again, specific resistance is rho. Okay, so first of all, expression for cell constant is L by A. L is the distance, A is the cross sectional area. Resistivity unit is ohm meter. Now let's talk about third question. Write the SI units for specific conductance and molar conductance. Specific conductance is what? Specific conductance is actually S meter inverse. Again, that is the kappa value. Okay, and molar conductance is S meter square mole inverse. I'll say the SI unit. Next, question number 4 is define molar conductivity and how does it vary with the increase in concentration of the solution. So molar conductivity, you can see the formula, the definition. It is the conductance of all the ions produced by 1 mole of an electrolyte when placed between two electrodes 1 meter apart. Okay, it is the conductance of all the ions produced from 1 mole of electrolyte. Okay, present in between the electrodes 1 meter apart. So lambda m formula is kappa by C. Okay, here you should remember that lambda m is equal to kappa into 1000 by C. Okay, provided this if the kappa is in S centimeter inverse. Okay, now if the kappa is in S meter inverse, then the formula of lambda m is equal to kappa by C into 1000. Okay, so please remember, this is important. Generally we'll be using this formula only, but you should know about this also. Next, how does it vary with the increase in concentration? So if you see, if concentration will increase, it is inversely proportional, molar conductivity will decrease. So molar conductivity decreases with the increase in concentration. It increases on dilution. Okay, if you increase the concentration, if you increase the dilution, means decrease the concentration, then molar conductivity will increase. Next, what is an electrolyte? Give an example of strong and weak electrolyte. So electrolyte is a substance which dissociates into ions in the aqueous solution or in the molten state and conducts electricity. Strong electrolyte is something which can ionize completely, example NaCl, HCl. Weak electrolyte which ionizes partially, example CH3COH or NH4OH. Next, why it is necessary to platinize the electrodes of a conductivity cell before it is used for conductance measurement. So platinization is important because it increases the effective surface area, okay, reduces the polarization of the electrodes, and it ensures that uniform current distribution takes place. Okay, so basically you need to write down any 2 points here. Increases the surface area, increases the polarization of the electrodes, and uniform current distribution takes place. Next, define the limiting molar conductivity and how it is related to molar conductivity of strong electrolyte. Okay. So limiting molar conductivity means, so we have understood that when concentration decreases, molar conductivity increases, right? So when you have decreased the concentration at infinite dilution, whatever is the conductivity, that is called as the limiting molar conductivity. Okay, so limiting molar conductivity is the molar conductivity of an electrolyte at infinite dilution, okay, where the interionic attractions become negligible and ions move independently. Next, how it is related to the molar strong electrolyte. So the molar conductivity increases with dilution and approaches a limiting value after infinite dilution. How it is related? The equation here is called as Debye-Onsager equation. Lambda m is equal to lambda naught m minus a root over of C. And this is only for strong electrolytes. And here A is a constant, whereas C is the concentration. Next, question number 8. Copper is conducting as such while copper sulfate is conducting only in molten or in the aqueous solution. Explain. Okay. Now see, copper metal, it is conducting in nature because of the presence of free electrons in that. But copper sulfate is an ionic compound and does not have free electrons in the solid state. When you have only copper sulfate, there is no free electrons involved. So when you molten or you take aqueous solution of that, it dissociates to give you ions, that is copper sulfate plus and SO4 2 minus, and hence these mobile ions can now conduct the electricity. Okay. Next question, which will have greater molar conductivity and why? Solution A, 1 mole of KCl dissolved in 200 cc of the solution. Solution B, 1 mole of KCl dissolved in 500 cc of the solution. Okay. Now, if you see what is concentration formula, number of moles by volume, right? If you see in solution A, okay, volume is less, that means concentration is higher. And in solution B, volume is more, that means concentration is less. So I can say that out of solution A and B, okay, if you see solution B, okay, solution B is less concentrated than solution A, okay, concentration wise, okay, and we have seen molar conductivity formula is what? Kappa into 1000 by C. So if less concentration, more molar conductivity. So that is why you can see that reason molar conductivity increases with dilution. Okay, in 500 cc of the solution, the concentration is lower than in 200 cc of the solution. Lower concentration, that means lesser interionic attraction and higher ionic mobility and higher molar conductivity. Okay, more is the dilution, lesser is the interaction between the positive and the negative ions, and they can move freely, and when they move freely they conduct better. Okay. Next is question number 10. In case of following pairs, which will have greater conduction of electricity and why? Okay, so we can solve this one based on that. Silver wire at 20 degrees Celsius and silver wire at 50 degrees Celsius. So if you see silver wire, this is a metallic conductor. So for metallic conductor, temperature increases, then the conduction decreases. Okay, at 20 degrees Celsius will conduct better. Reason, in metals, the resistance increases with the increase in temperature and the flow of electrons will be restricted, so the conduction will decrease. NaCl at 20 degrees Celsius and same NaCl at 50 degrees Celsius. So this will be NaCl at 50 degrees Celsius because NaCl is an electrolytic conductance. So it is an electrolyte, and with the increase in temperature, the mobility of the ion increases, and that is why the conduction or conductivity increases. Next, NH4OH at 20 degrees Celsius and NH4OH at 50 degrees Celsius. Again, NH4OH at 50 degrees Celsius because this is a weak electrolyte, and increasing the temperature increases not only its ionization but also the mobility. Next, 0.1 m acetic acid, 1 m acetic acid. Always 0.1 m acetic acid. That is because of lesser concentration. It is a weak electrolyte. When you dilute it, the degree of ionization increases for weak electrolytes. Hence, the molar conductivity also increases. Next, write the Debye-Onsager equation and mention the various terms. So we have already written this one. Lambda m is equal to lambda naught m minus a root over of c. Lambda m is molar conductivity. Lambda naught m is limiting molar conductivity. A is a constant and c is the concentration of the electrolyte. Next, question number 12. What is the effect of temperature on molar conductivity? So as the temperature increases, the molar conductivity increases. The reason, because here is the mobility of the ions increases, and for weak electrolyte their dissociation increases, and that also leads to the higher molar conductivity. Okay, so when you increase the temperature, in case of strong electrolytes, the speed of the ions, the speed in which the ions are moving, that increases. But for weak electrolyte, what happens? For weak electrolytes, the ionization increases, and that is why the molar conductivity increases. Next, what is the effect of dilution in conductivity and molar conductivity? So this is a very, very important question. So on conductivity, what happens? Like when you dilute it, the conductivity decreases, but for molar conductivity, it increases. So now, first of all, effect of dilution on conductivity. It decreases on dilution because the number of ions per unit volume decreases. Conductivity definition is how much ions are present in per unit volume. Their conductivity is called as kappa value. Now, when you dilute it, the number of ions per unit volume decreases because the ions will start moving. Can move freely now, right? So when they move freely, the number of ions per unit volume has decreased, and when this decreases, conductivity decreases. Now, molar conductivity, as you see from the formula, it is inversely proportional to concentration. So it will increase on dilution because the ionic mobility increases and interatomic attraction also decreases. Next, why lambda m for CH3COOH cannot be determined experimentally, the limiting molar conductivity, right? So you can see what happens. CH3, if you see the graph, it is like this. This is for strong electrolyte, and for the weak electrolyte, the graph is like this. It never touches the y-axis. So we cannot extrapolate and find the value. So CH3COH is a weak electrolyte and does not completely ionize even at the highest dilution. So therefore, its molar conductivity does not reach a constant value experimentally. Okay. So hence, the CH3COH value cannot be determined directly, and it is calculated using the Kohlrausch law. Next, question number 15. Out of HCl and NaCl, which do you think to have the greater value of lambda naught m and why? Okay, now if you see the conductivity, the electrolytic conduction depends on the size of the ions, okay? Cation size and anion size. If you see, anion is same in both the case, but cation is H plus here and Na plus here. H plus is smaller size, so it can move faster, and that is why the conductivity will be highest in HCl. The reason, HCl contains H plus ions which have very high ionic mobility compared to Na plus ions in NaCl because of the size only. Next point, 1 m aqueous Na2SO4 is diluted by adding water. What will happen to the value of its conductance, conductivity and molar conductivity? Okay. Now see, conductance is what? 1 of inverse of resistance, right? So when you conductance is equal to 1 by R. So now conductance value will actually decrease here. Okay. Next is conductivity value will also decrease, as we have seen the number of ions per unit volume, and molar conductivity will increase. Clear? Next, give reason that conductivity of an electrolyte solution decreases with the decrease in concentration. Already we have discussed this question. Number of ions per unit volume decreases, so that is why the conductivity decreases. Next, Kohlrausch law and its application already discussed. I'm not going to repeat it. You can see it is that at infinite dilution, the molar conductivity of the electrolyte is the sum of its individual ions. Next, mention any three factors on which the electrolytic conductivity depends. So there are so many important factors. First is the concentration, nature of the electrolyte, strong electrolyte or weak electrolyte. Then we have temperature. Okay, this is also very important. Conductivity increases with the increasing temperature. Next, 20th question. The curves obtained when molar conductivity is plotted against the square root of concentration for two electrolytes A and B are shown. What can you say about the structure of the two electrolytes A and B? How do you account for the increase in the molar conductivity of electrolytes A and B on dilution? Okay, so definitely A, you can see this is a strong electrolyte and B is a weak electrolyte. How will you account for the increase in molar conductivity? For strong electrolyte, it is due to the increase in the mobility of the ions, right? Mobility of ions. And in case of weak electrolyte, it is mainly because of the increase in the dissociation of the electrolyte to produce more ions. So you can see electrolyte A shows a straight line decrease of lambda m with C. So A is a strong electrolyte and B is a weak electrolyte. Okay. Next is depending on the magnitude of conductivity of materials, mention the three types of materials with an example. So we have conductors, semiconductors and insulators, right? So conductors with higher conductivity, copper, silver; semiconductors with intermediate conductivity, silicon, germanium; and insulators with least conductivity, right, rubber or glass. Okay. Now we will do question from electrolytic cell. State Faraday's first and second law of electrolysis. This is also important question. Okay. Give its mathematical expression and mention any two factors that determine the product of electrolysis. So let us see the first answer now. State Faraday's first law. So Faraday's law is used in the electrolytic cells. Here electrical energy is converted to chemical energy. So what we can say that the mass of substance deposited, okay, or liberated at the electrode is directly proportional to the quantity of electricity passed through the electrolyte, or M is proportional to Q, or M is equal to ZQ, or this can be written as M is equal to Z into I into T, where Z is your electrochemical equivalent, I is the current and T is the time. Then Faraday's second law, this is used when you have two cells connected in series. Okay, when the same quantity of electricity is passed through different electrolytes, the masses of substances deposited are proportional to their equivalent weights. M1 by M2 is equal to E1 by E2. Next is question number 3 here. Sorry, we haven't completed question number 1. State the factor which depends the products of electrolysis. So it depends on the nature of the electrode and the nature and concentration of the electrolyte. Next is question number 2. Define electrochemical equivalent and how it is related to the equivalent weight of the element. Now see, electrochemical equivalent, it is the mass of the substance. So if you see what is Z, M is equal to Z into I into T, right? Z is equal to molar mass divided by N into 96500 into I into T. Okay, so what is Z is, if I take I equal to 1 ampere and time is equal to 1 second, then whatever is mass deposited when 1 ampere of current is passed for 1 second, that is called as Z value. So it is the mass of the substance deposited or liberated by passing 1 coulomb of electricity through an electrolyte, and the relation between the, what is the relation question is asked about, how it is related to the equivalent weight of the metal. So now you see Z is equal to molar mass by N into 96500. Okay, and this M by N, okay, that is your equivalent weight. So E by 96500. So Z is equal to E by 1 Faraday here. Next is question number 3 here. How much substance is deposited by 1 coulomb and what it is called? Okay, so the mass of the substance deposited by passing 1 coulomb of electricity is called as electrochemical equivalent and it is denoted by Z. Okay, why does the electrolysis of NaBr and NaI give Br2 and I2 respectively, while that of NaF gives you O2 instead of F2? Okay, now see, so the products of electrolysis depends on the reduction potential. Okay, in aqueous solution, Br minus and I minus are easily oxidized as compared to water, hence they give you Br2 and I2. But F minus, for F minus, it is very difficult to get oxidized due to its high oxidation potential. Okay, that means F minus has they cannot lose electrons. Their size is so small, they're highly electronegative, so it is very difficult for F minus to lose electrons and get converted to F2. So water gets oxidized instead of producing oxygen. Okay, so 4OH minus gives you O2 plus H2O plus 4 electron. Hence NaF gives you O2 instead of F2. Next, question number 5. How much electricity is required in coulomb for the oxidation of H2O to O2? So if you see, okay, H2O, 1 mole of H2O to O2. So exactly O2 minus is getting converted to O2, right? If I just balance it, so 2O2 minus gets converted to O2. So total how many electrons are required here? If you see, 1 O2 minus loses 2 electrons. 2 O2 minus will lose 4 electrons. So the total number of electrons that is needed here is 4 moles of electrons. Next, 1 mole of FeO2, Fe2O3. Again, if you see here, the oxidation state of Fe is plus 3, right? But there are 2 Fe are considered here, right? 2 Fe is there. So you can see 1 mole of FeO2, Fe2O3. Here Fe oxidation state is plus 3, plus 2, and in Fe and Fe2O3 is plus 3. So you are just taking 1 mole of electrons, or I can say it is 96500 coulombs. Here also 2 moles of electrons. 2 moles of water requires 4 moles of electrons. So 1 mole will require 2 moles of electrons. So you can just convert it into coulomb by multiplying it with 96500. Next is 1 mole of aluminium. This one is super easy. 1 mole of aluminium to aluminum. So here 3 Faraday or 3 moles of electrons are required. So 3 into 96500. Cu plus 2 Cu, 2 moles of electrons. So 2 into 96500 plus 7 to plus 5, 5 moles of electrons. So 5 into 96500. Next is 7th question. The following electrochemical cell has been set up. Okay, so here you see platinum 1, Fe2 plus, Fe3 plus is there. Means here there is oxidation. Then Ce plus 4 to Ce plus 3 with platinum electrode. This is the reduction part. So this whole part is one cell, right? And E0 of Fe plus 3 is given. E0 of Ce plus 4 is given. If an ammeter is connected between the two platinum electrodes, predict the direction of flow of current. Will the current increase or decrease with time? Okay, now if you see, this is the oxidation part and this is the reduction part. Means this one is your anode and this one is your cathode. If you see, the reduction potential is also like that. Cathode is having higher reduction potential, so electrons will flow from this to this. Current will flow from cerium to iron, right? So direction of current will be from cerium electrode to iron electrode. Okay, then current with time, it decreases with the time due to the decrease in cell potential. Next, we'll talk about products of electrolysis. On electrolysis of an aqueous solution of NaCl, why H2 and not sodium is liberated at the cathode? So it again depends on the reduction potential. Okay, so if you see, in aqueous solution of NaCl, you have both Na plus ions and water molecules are present. At cathode, the species with lower reduction potential is discharged first. Okay, so if you see in sodium, the sodium reduction potential is minus 2.71 volt, and for water it is minus 0.83 volt. Okay, so if you see, this is having higher reduction potential, so that means the tendency for the reduction of H2O to H2 is higher. Since water has a higher reduction potential than Na plus, so water gets reduced preferentially. Okay, water gains electrons and gets converted to H2 plus to OH minus. Therefore, H2 gas is liberated instead of sodium metal at the cathode. Next, give the products obtained at each electrode respectively when molten NaCl, aqueous NaCl and acidulated water undergoes electrolysis. Okay, so for molten NaCl, sodium is formed for anode and chlorine is formed at the, sodium is formed at cathode and chlorine is formed at anode. Aqueous, aqueous NaCl, H2 gas is formed at cathode and Cl2 gas is formed at anode. Then acidulated water, okay, just a minute. One second. Okay, here one more term is there. Acidulated water undergoes electrolysis. So for here I'll just mention oxygen will be formed at anode, okay, and hydrogen gas will be formed at the cathode. Okay, next one, give the following information about nickel-cadmium storage cell. Okay, what is the electrolyte used here? The concentrated potassium hydroxide is used. Reaction involved at anode and cathode. So at anode, cadmium undergoes oxidation and at cathode, nickel undergoes reduction. Okay, Here there is a reaction for oxygen as well. So nickel hydroxide gets converted, nickel OH gets converted to nickel OH whole 2. Approximate voltage of the cell is 1.2 volt. Material of the cathode is here nickel oxyhydroxide, and material of the anode is cadmium. Okay. Next is one second. Okay, next question is, give reason why does a dry cell becomes dead after a long time even if it has not been used. So see, a dry cell becomes dead even when it is not in use due to the slow internal chemical reaction. There's a self discharge that takes place. Zinc container slowly reacts with the electrolyte. Manganese dioxide and ammonium chloride undergo slow reactions, and this consumes the active material and reduce the cell potential, and hence the cell becomes dead because of self reaction. Next, write a note on dry cells and mercury cells. Okay, so dry cell is a primary cell, mercury cell is also a primary cell. Here anode is zinc container, here it is zinc amalgam. Here cathode is carbon rod surrounded by MnO2, here it is HgO mixed with carbon. Electrolyte is a paste of NH4Cl and ZnCl2, here it is KOH or NaOH. Voltage is 1.5 volt, here it is 1.35 volt. Decreases, nature of the voltage is decreases with use, it remains constant throughout the life. Torches, radios, and it is used in clocks, whereas this is used in hearing aids, watches, and cameras. Next, write the role of ZnCl2 in the dry cell. This is important question. Okay, ZnCl2 is added to prevent the accumulation of NH3 gas, because then what will happen? Because this helps to increase the life of the cell, and how it maintains the concentration of NH3. It forms a complex with NH3. Okay, so that is why ZnCl2 is used. Why does a mercury cell gives a constant voltage throughout its life? So here we have written, right, if you see, mercury cell gives a constant voltage throughout the cell. So what happens in mercury cell, both the reactants Zn and HgO are solids. Okay, electrolyte concentration remains almost constant during the operation, hence the EMF of the cell also remains constant. Next is, what are batteries, and mention the type of batteries. A battery is a combination of two or more cells connected together to supply the electrical energy. Two types of batteries are primary batteries and secondary batteries. Primary batteries are non-rechargeable dry cell mercury cell, and secondary batteries are the rechargeable batteries, lead battery and nickel-cadmium battery. Next is, write a cathodic and anodic reaction of the lead storage battery at both discharge and recharge process. So you can see the anode reaction during discharge, lead gets oxidized to lead sulfate, and cathodic reaction, lead oxide gets converted to Pb2 plus. During recharge, what happens? The reverse reaction takes place at anode. This one PbSO4, at anode there is reduction, so lead sulfate gets converted to lead 0, Pb0, and at cathode the reduction oxidation takes place where Pb plus 2 gets converted to Pb plus 4. Next, write the overall nickel cadmium battery and mention the anode and cathode of it. So here if you can see, anode is the cadmium, cathode is nickel oxyhydroxide, and the overall reaction is like this. Okay, so now let's see question from fuel cell. Write a neat diagram for H2O2 fuel cell and express its cathodic and anodic reaction. So first of all, you can see the diagram here. At anode we have to take hydrogen, and at cathode we have to take oxygen. Then at anode, hydrogen undergoes oxidation to produce water, and at cathode oxygen undergoes reduction to produce 4OH minus. Then you can add this reaction to get the overall reaction. Okay, next, what are fuel cells? This is very important question, we have already discussed. Okay, so I'm not repeating it again here. So fuel cells are those in which the the chemical energy of combustions are converted to electrical energy. Okay, now let's move to corrosion questions. Describe any two techniques used for preventing the corrosion of metals. You can write any two. You have painting, we have galvanization, or we can use even cathodic protection. So in galvanization, what happens? Iron is coated with a thick layer of zinc, and zinc acts as a protective layer and also as a sacrificial metal, preventing the rusting of iron. So zinc is having more oxidation potential, it gets reacted faster, and it protects the iron rod. Now, cathodic protection is what the metal to be protected is made the cathode by attaching a more reactive metal like zinc or magnesium, which corrodes instead of the iron. Okay. Next is, explain corrosion is an electrochemical phenomena. This is important question. Okay, so what happens? Corrosion occurs due to the formation of tiny electrochemical cell on the electrical surface, on the metal surface, in the presence of moisture or oxygen. So you can see here. So what happens? Fe from any particular rod, okay, it gets oxidized, releases 2 electrons and form Fe2 plus. Okay, and that 2 electrons now move, okay, and get reacts with oxygen and water to produce 4OH minus. The electrons flow from anode to cathode, causing oxidation and reduction reactions simultaneously. Hence, the corrosion is an electrochemical phenomena. Next is rusting of iron is quicker in saline water than in ordinary water. Explain here. So see, saline water contains dissolved salts, right, which increases the electrical conductivity of the water. The conduction increases. This facilitates the faster movement of electrons between the anodic and the cathodic region. There are two regions in the metal itself, right? So when you have this saline water, the movement of these electrons becomes faster. As a result, the electrochemical reactions occur more rapidly, increasing the rate of the rusting. Next, we can use aluminium in place of zinc for cathodic protection of rusting. Comment. So definitely aluminium is also more reactive than iron, so we can use it, right? Aluminium is more reactive than iron and has a more negative electrode potential than iron. So technically, if I speak, aluminium can act as a sacrificial anode and protect the iron from the corrosion. But what is the problem in aluminium? That it forms a thin oxide layer, that is aluminium oxide, which reduces its effectiveness. Right now, if the rod is there that is getting converted to aluminium oxide, then the cathodic protection decreases here. So hence that is why zinc is preferred over aluminium. Next, what is corrosion, and mention the factors which affects the corrosion. So corrosion is the slow and continuous destruction of a metal by chemical or electrochemical reactions with its environment. And what are the factors of corrosion? Nature of the metal and the presence of moisture and oxygen. These are the two important factors. Next, give reason that rusting of iron pipe can be prevented by joining it with a piece of magnesium. So this is your sacrificial protection, or we can say galvanization. Magnesium is more reactive than iron and has more reduction potential. So that is why when magnesium is attached to the iron or covered with it, magnesium acts as a sacrificial anode and gets oxidized instead of iron, right? So this iron becomes the cathode and is protected from rusting. Next, iron pipes are usually coated with zinc. The same reason, zinc is more reactive than iron. So when iron is coated with zinc, that is called as galvanization. Zinc prevents the corrosion of iron with air and moisture. And even if the coating is damaged, zinc corrodes first and protects the iron by sacrificial protection. Next, why is zinc better than tin in protecting the iron from corrosion? So zinc is more electropositive or more reactive than iron, whereas tin is less reactive than iron. So if you use tin in place of zinc, if you have a combination of tin and iron, then iron will be the anode and that will start oxidation faster and that will corrode faster. Okay, so if zinc coating is broken, zinc still corrodes first and protects the iron. But if tin coating is broken, the iron corrodes faster because it is less reactive. Okay. Next is a very interesting question. 3 iron sheets have been coated separately with 3 metals A, B and C whose reduction potentials are given below. Identify in which case the rusting will take place faster when the coating is damaged. Now see, iron reduction potential is minus 0.44 volt, right? So we need something which will have lesser reduction potential than iron. Then only it can undergo oxidation and iron will be behaving as a cathode. So if you see A here, it is having lesser reduction potential than iron. That means if I take A and iron, then A will undergo oxidation. Similarly, if you see B and iron, then B will undergo oxidation. But if you see C is having lesser reduction potential, right? So that means what? C will undergo oxidation faster than iron. It cannot protect iron. Okay, so C is having higher reduction potential than iron. That means if here there is a combination of C and iron, then iron will undergo oxidation faster. Okay, because C reduction potential is higher, so C cannot be used here. So you can see when the coating is damaged, the metal with more positive electrode potential than iron acts as cathode and iron becomes the anode. Iron corrodes faster. That happens in the case of iron. E naught value is minus 0.44 volt. So compare it with the coated material. So if you see A, it is having more negative than iron, that means it will protect iron. B also, it is more negative than iron, it will protect iron. In fact, it will be the best protection because it is having a very high reduction potential, very low reduction potential. C, if you see, it is more positive than iron. So when iron becomes anode and rusting will increase. Okay, now rusting will take place faster when iron is coated with metal C. Okay, now we will do some numerical questions that have been asked in the previous years. So the first question here is, a solution of nickel nitrate is electrolyzed between the platinum electrodes using a current of 5 amperes for 20 minutes. What mass of nickel is deposited at the cathode? Molar mass of nickel is 58.7 gram per mole. Now this is very simple and easy question from Faraday's first law, right? What does Faraday's first law say? M is equal to Z. Okay, just a minute. 1 second. I'll erase this one. Okay. Okay, now let me write over this. So we know that M is equal to Z into I into T, right? What is Z value? Z is equal to molar mass, right, divided by N. into 96500 into I into T, right? So what is the value of molar mass here? For nickel it is 58.7, and if you see nickel is in +2 state, okay, it will gain 2 electrons and it will get converted to nickel. So here n is 2 and here we have 96500, then we have I is equal to 5, then I have 20 minutes and we have 60 seconds. The minutes should be converted into seconds. Now if you solve this, you will get around 1.82 grams. Next, the second question here is if a current of 0.5 ampere, so I here is 0.5 ampere, flows through a metallic wire for 2 hours. So 2 into 60 into 60 seconds, right? How many electrons will flow through the wire? How many electrons will flow through the wire? So you can easily calculate this one. See, Q is equal to I into T and Q is also equal to N into E. Okay, so I into T and N into, so I can equate this one equation and the second equation. N total, Q is equal to N into E. N is the number of electrons, E is the charge of each electron. So now if I just solve this, I into T is equal to N into E, and I have to calculate N, so that is equal to I into T divided by E. I value is given to me 0.5 amperes, 2 hours means 60 minutes into 60 seconds, divided by E is 1.6 into 10 to the power of minus 27 charge, that is the charge of 1 electron. Now if you solve this, you will get 2.25 into 10 to the power of 22. Next, the conductivity of 0.001028 moles per liter acetic acid. So first of all, concentration is given to you how much? 0.001028 molarity, okay, of acetic acid. Conductivity value means the kappa value 4.95 into 10 to the power of minus 5 s centimeter inverse. Calculate its dissociation constant, okay. If the limiting molar conductivity is 390.5 s centimeter square mole inverse. Okay, so first of all, what we need to calculate? The degree, calculate its dissociation constant. For that I need alpha value, but to calculate alpha value I need the molar conductivity value. So first I'll calculate molar conductivity value, which is kappa into 1000 by C. So kappa value is 4.95 into 10 to the power of minus 5 into 10 to the power of 3 divided by 1.028 into 10 to the power of minus 3. Okay, now if I solve this, I'll get the value of molar conductivity, which will be around 48.15 s centimeter square mole inverse. Okay, now next thing is to calculate alpha, which is equal to lambda m by lambda naught m. Okay, now this one will be 48.15 divided by 390.5. Okay, now if I solve this, I'll get around alpha value as 1233. Next thing is to calculate the dissociation constant. Ka is equal to C alpha square by 1 minus alpha. C value is how much? 1.028 into 10 to the power of how much? I'll get minus 3, right? 1, 2, 3. Minus 3 into alpha square is 0.1233. I'll write 0.123. Alpha square by 1 minus 0.123. Okay, now if I solve this, I'll get 1.78 into 10 to the power of minus 5. Now coming to question number 4 here, the conductivity of 0.241 m ethanoic acid. So let us write the concentration, that is 0.0241 m ethanoic acid is, the kappa value is 7.896 into 10 to the power of minus 5 s centimeter square mole inverse. Okay, calculate the molar conductivity. Okay, calculate the molar conductivity if the limiting molar conductivity of the ethanoic acid is 390.5. Okay, what is the degree of dissociation? Very similar question. First we will calculate the molar conductivity. Its formula is kappa into 1000 by C. So kappa value is 7.896 into 10 to the power of minus 5 into 1000 by C value is how much? 0.0241. Now if you solve this, you will get lambda value as 3.28 s centimeter square mole inverse. Now if I want to calculate now alpha, 3.28 by 390.5. Okay, so almost it will be 0.0084. Okay, now let's solve question number 5. So calculate the equilibrium constant for the given reaction. The standard reduction potentials are given to you for Fe3 plus and I2 minus to I2. Okay, so I'll just tell the value here. First of all, if you can see that we have Fe plus 3 to Fe plus 2. Okay, the value given here is 0.77 volt, and I minus to I2, the value given to me is 0.54 volt. Okay, so definitely this is my reduction thing. So this is cathode and this is anode. Okay, so what is E naught of the cell here? E naught of the cell is cathode minus anode. So 0.77 minus 0.54. So I will get 7 minus 4, 3, 0.23 volt. Okay, now what is the N value? You can see here 2 Fe is there, right? So from +3 to +2, 1 electron will be lost. For 1 electron will be gained. For 2 iron, 2 electrons will be gained. Similarly, I minus to I2, 1 electron will be lost. For 2 iodine, 2 electrons will be lost. So N is equal to 2. So what is the value of delta G here? Minus NFE naught of the cell. That is equal to minus 2 into 96500 into E naught of the cell is 0.23 volt. Now this gives me the value of around log, one second, the question has asked me to find out equilibrium constant. Okay, not delta G, sorry, just a minute. So I'll write down here, small error will do here, one second. Okay, so what's the formula? E naught of the cell is equal to 0.059 by 2 log of K, and that gives me 0.23 volt into 2. Okay, 0.059, I can write down 0.06 is equal to log of K, and this gives me log K value as 7.78. Okay, so log K is equal to 7.78. Now what is the K value? K value is 10 to the power of 7.78. Now we can solve it as 10 to the power of 7 into 10 to the power of 0.78. Okay, now if you take this anti-log of this one, you will get 6 into 10 to the power of 7. Okay, you can also remember log 3 value is somewhere around to 0.78. Okay, next let's move to question number 6 here. Calculate the EMF of the cell in which the following reaction takes place. So this is your direct Nernst equation question. Okay, so first of all, let us write the reaction. So what is the reaction? 2Ag plus, okay, plus Mg is also there, okay, gives me Mg2 plus 2Ag. Okay, so Ag plus concentration is 10 to the power of minus 4, okay, and Mg2 plus concentration is 0.2 molar. Okay, E naught value is how much? 3.17. Okay, E value is equal to E naught minus 0.059 by N log of magnesium 2 plus divided by Ag plus to the power of 2. Okay, now E naught value is 3.17 minus 0.059 by 2. Okay, so number of electrons you can easily see it is 2. Log of Mg2 plus concentration is 0.2, silver concentration is 10 to the power of minus 4 to the power of 2. Okay, now if you solve this, you will get 3.17 minus 0.059 by 2 log of, I can write down this is minus 8, right? It goes up, it will become plus 8. But if I write down, it can write 2 into 10 to the power of 7. Okay, now you can easily solve this and answer will be around 2.95 volt. Next question, the standard electrode potential for a cell is already given. Calculate the Gibbs free energy. Okay, this is very simple question. Directly E naught value is given to you, which is 0.235 volt. Just calculate delta G value. N of the reaction is again 2. You can see here 2 into minus NF E naught, right? 2 into, and E naught value is 0.235. So if I solve this, we'll get minus 45.36 volt. Next question, the EMF of the cell. Okay, just a minute. The EMF of the cell corresponding to the given reaction is 0.28 volt. Write the half cell reactions and calculate the pH of the solution at the hydrogen electrode. Okay, now if you see this particular reaction, okay, if I just write down the reaction here, so you can see E of the cell will be equal to E naught of the cell minus 0.0591, okay, by N log of product side I have Zn2 plus concentration divided by H plus concentration. Okay, now N value is how much here? Zn gets converted to Zn2 plus, H plus gets converted to H2, so N value is 2 here. E naught value is equal to 0.28 volt. Okay, it is already given. The EMF of the cell corresponding to the given, okay, E value is given, sorry, E value is given to me. Okay, next is Zn2 plus concentration is given to me as 0.1 molar, okay, and H plus concentration is not given. Now if you see E naught value here, what is the oxidation is for zinc, right? Anode is zinc, and cathode is hydrogen, right? So I can write E naught of the cell is cathode minus anode, so 0 minus, for zinc it is minus 0.76. That gives me plus 0.76 volt. So now if I solve this one, I'll get 0.28 is equal to 0.76 minus 0.059. I'm just taking 0.06 for easy calculation. Log of Zn2 plus concentration is 10 to the power of minus 1 divided by H plus concentration to the power of 2. Now solve this and first find the H plus concentration. Okay, you will find the H plus concentration to be 2.37 into 10 to the power of minus 9 molar. Okay, so once you have found this one, next thing is to find the pH. So what is, I'll just put a line here. See what I've got, H plus concentration is 2.37 into 10 to the power of minus 9 molar. Then what is pH? pH is equal to minus log of H plus concentration, right? So I can write down minus log of 2.37 into 10 to the power of minus 9. That can be written as minus log of 2.37 plus log of 10 to the power of minus 9. Okay, now see, log of 2.37, this can be written as like log of 23. You have to check in the log table like this. See, 23 with 7 value. Okay, 1 2 3 4 5 6 7, this is 3.729. okay, so in that you have to put a decimal, so 0.3729. okay, 0 1 2 3 4 5 6 7. Okay, not this one, sorry, this value 3747. okay, it starts from 0, so I'll erase this one. This is 3747. okay, 3747. Actually this starts from 0 1 2 3 4 5 6 and then 7. So here you have to say it is 0.3747 and log of 10 to the power of 9 is minus 9. Now if I solve this, here I have outside one log, so if I solve this you will get around 8.63. okay. Okay, so students, these were the most important questions from electrochemistry, which we have already discussed. Now, the most important thing is, as I told you, this particular session, this particular time, this last moment is very, very important. And if you need any kind of guidance, any kind of mentorship, do reach out to me. We can have a one-to-one discussion. The link for the mentorship session is there in the description section. So please go and register yourself and then we can have a one-to-one discussion. Okay, so thank you so much for watching and all the best. Keep learning, keep working hard. Exams are very, very close, and keep smiling.